So let's continue our lecture video in hydraulics under the topic pipes. Now in this video, we will solve the sample problems number 5 to 8 in the handout. Here is our example number 5. The flow from point A to point E is 280 liter per second. Using roughness coefficient N is equal to 0.011, compute for letter A, the value for the flow rate at the pipe number 4, or that is the Q sub 4. Letter B, find the value for Q sub 5. And C, find the value for head loss from A to E, or that is the total head loss. Now given here are the length and diameter of the different pipes in this connection. So find the value for Q4 first. So we can derive different equations from this setup. So let's start with the flow rate, the discharge. For the flow rate 1, or the discharge at 1, that is equal to the discharge 4 plus the discharge at 5 plus 2, or plus 2 plus 5. So 4 plus 2 plus 5, that is equal to 1. And since 1 here is equal to 6, and we have here the total flow as 280 liter per second, or that is 0.28 cubic meter per second. So that is also equal to Q sub 6, and that is equal to 0.028 or 0.28. So that is for equation 1. Now equation 2, we have here Q sub 3. Here the flow here for pipe number 3, that is equal to the combined flow from 2 and 5. So Q sub 3 is equal to Q sub 2 plus Q sub 5. And that is our second equation. Next, we have here the flow here at 6. So the discharge at 6 is equal to the combination or the combined flow from pipe 4 and pipe number 3. So if this is pipe number 4, the flow from pipe number 4, and then pipe number 3, that is equal to 6. So that is Q sub 6 is equal to flow or discharge at 4 plus discharge at pipe 3. So this is equation number 3. And actually this is equal to 0.28. So this is equation 3. So what's next will be the head loss. For the total head loss, that is head loss at 1 plus head loss at pipe 4 plus head loss at pipe 6, and that is our equation 4. So head loss here. Next, again, head loss. So for the head loss in pipe 4, that is equal to the head loss of 2 and 3. Okay, so head loss of pipe 4 is equal to the total head loss of 2 and 3. So that is equation number 5. So what else? So another thing here is this parallel connection here. 2 and 5 is parallel with each other. Therefore, we have HF2 equals HF5. And this is our equation 6. So we have 6 equations formed. Now as for head loss, what we're going to use here, since we are given the roughness coefficient n, so we're going to use the Manning's formula, 10.29. So Manning's, which wherein HF is 10.29n squared LQ squared all over D raised to 16 over 3. So this is Manning's formula. So since we have all the equations, so what will we do here? We need to find the value for Q4. So how will we do that? To find the value of Q4, so we will need to see the relationships here. So which of these equations are we going to use? So we have here, we don't have value for head loss, total head loss. So we can stick to this, the first equation, since we have Q4 there. Therefore, we need to do something about Q2 and Q5. So for Q2 and Q5, we can use the relationship here at equation 6. And we can also use the relationship here at 5. But then to remove Q3 here, so to remove Q3, we need the relationship here at 3. Okay. So since we have Q6 and Q1 equal to 0.28, there's no need to look for the values of Q1 and Q6. So from this 6 here, we can get the value for Q2 in terms of Q5. So we'll get the values for Q2 in terms of Q5, and then we will jump to this one here. So since we will have Q2 in terms of Q5, we will get the value for Q3 in terms of Q5. Since we are going to get the value of Q3 in terms of Q5, so in this equation number 5, so here the Q2 here is in terms of 5, the Q3 is in terms of 5, so we can get the values for Q4 in terms of 5. So we will all substitute here in equation 1 our Q4 in terms of Q5, Q2 in terms of Q5, and then we will let Q5 here. So we will first determine the value for Q5. After determining the value of Q5, we will finally get the value for Q4. So it means we will get the value of Q5 first before getting the value of Q4. Okay, so that's our plan for this problem. So first, let's get the value for Q2 in terms of Q5. So at 6, so at equation 6, wherein the relationship here is HF2 is equal to HF5. So from this formula, we can cancel out the constant 10.29. And since they all have the same value for roughness coefficient, we can now cancel this out. Therefore, what remains here is L2 Q2 squared or let's just substitute it straight. What is value for 2, 360, and 250? So 360 Q2 squared all over 250. So raised to 16 over 3 is equal to, what's the value for 5? That is 600, 200. So we have here 600 Q5 squared all over 200 for the diameter. So Q2 is now equal to square root of 600 times 0.25 raised to 16 over 3. And then we have 360 times 0.2 raised to 16 over 3. So that is 2.341. So 2.341 Q5. So this becomes our equation 7. Next, we will get the value for Q3. So from 6, let's go to the value for Q3 in terms of 5. So at equation 2, wherein Q3 is equal to Q2 plus Q5, we have here Q3 equals 2.341 Q5 plus Q5. So Q3 is equal to 3.341 Q5, and that is equation 8. Again, since we now have our Q2 and Q3, what's next? So here at equation 5. So at equation 5, we have there HF4 is equal to HF2 plus HF3. So we can already cancel out again the 10.29 and n squared here. So what's left will be the length of 4. Length of pipe 4 is 1/4 and the diameter 300. So length is 1,400 Q4 squared all over 300. 0.3 raised to 16 over 3 equals our HF2 here is 360 Q2 squared all over 0.25 raised to 16 over 3 plus our 3. Pipeline 3 is 300 to 50. That is 300 Q3 squared all over, that is 25 to 50. 16 over 3. Now, since our Q2 is equal to 231, so we will now substitute here the value for Q2. So our Q2 here becomes 2.341 Q5 squared. Then for our Q3, that becomes 3.341 Q5 raised to 2. So we can now we can now have here the value for Q4 in terms of Q5. So that will be, let's reduce it first. 860, 626. So 860, 626 point, so 860, 626.426 Q4 squared equals, so 860, 626, 426, 8. And then that is equal to 360 times 2.341 squared, 0.25 raised to 16 over 3 plus 300 times 3.341 squared all over 0.25 raised to 16 over 3. So 650, 230.126 Q5 squared. So what's now the value for Q4? So Q4 is equal to square root of 650, 230.126 all over 860, 626.426. So 3.17 Q5. So this is equation 9. So using this Q4, let's now substitute this 7, 8, and 9. So substitute them to equation 1. No, it's just only 7 and 9 only for equation 1. So substitute 7 and 9 to 1. Our 1 here, equation 1 is Q4 plus Q2 plus Q5 is equal to 0.28. So Q4, that is, so Q4 plus Q2 plus Q5 is equal to 0.28. Q4 is 3.17 Q5 plus Q2 is 2.341 Q5 plus Q5 equals 0.28. So Q5 is equal to 0.28 all over 3.17 plus 2.341 plus 1. So that is 0.28. So 0.043 cubic meter per second. 0.043 cubic meter per second. So that's for Q5. Now we need the value for Q4. So Q4 is equal to 3.17 times 0.043. So 3.17 times 0.043 is equal to 0.136. Q4 is equal to 0.136 cubic meter per second. So for letter C, we're looking for head loss from A to E. So head loss, so at equation 4 here, for letter C, head loss is is equal to HF1 plus HF4 plus HF6. So head loss is equal to 10.29 times 0.011 squared. So for HF1, so our pipeline 1 is 300 meter length and 450 mm diameter. So 300. And the Q is 0.28 squared. So 0.45 raised to 16 over 3 plus HF4. For our HF4 is 360 and HF4, so sorry, HF4 is 1,4, so 1,4 and 300. So 1,400 Q 0.136 squared all over the diameter of 300 plus HF6. What's that? 600 and 450. 600, 450. So 600 flow of 0.28 all over 450. So head loss is equal to 0.28 squared, 0.45 raised to 16 over 3 plus 1,4 times 0.136 squared all over 0.3 raised to 16 over 3. Next, plus 600 times 0.28 squared all over 0.45 raised to 16 over 3. So 26.03. Head loss, total head loss is equal to 26.03 meters. So that's for example number 5. Now let's go to example number 6. Two pipes are connected in parallel between two reservoirs as shown. Data are as follows. Pipeline A and pipeline B have length 2,600 meters and 2,400. They have diameters 1,300 mm and 900 mm. And the coefficient C of 90 and 100. Compute for letter A, Q sub A, B, Q sub B, and letter C, the length of a single pipeline having a diameter of 1,000 mm to replace A and B with the coefficient of 120. So this is the system. So there are two reservoirs, 1 and 2 reservoir, and two pipes connect these two reservoirs, pipes A and B. So first, let's compute what's the value of QA. So that is, from this relationship, you can see that A is parallel to B. So HFA, so you can see that HFA is equal to HFB. And this is equal to the total head loss of 3.8 meters. So since we are given here the coefficient C, the formula that we're going to use here is the Hazen-Williams formula. So this one here. So the Hazen-Williams formula for letter A, HF is equal to 10.64 LQ raised to 1.85 all over C 1.85 D raised to 4.87. So that is Hazen-Williams. So substitute here the value for head loss for A. So for A, we have 3.8 total head loss, 10.64. The length of pipeline A is 2,600 and missing QA, 1.85. All over C, here is 90 raised to 1.85. The diameter here is 1,300 raised to 4.87. So QA is equal to 3.8 times 90 raised to 1.85 times 13 raised to 4.87 all over 10.64 times 2,600 raised to, so that is this one here, the diameter. So the diameter here is 1.3 meter. So 1.3 meter. So therefore our Q sub A is 1.467. So 1.467 cubic meter per second. So that is QA. Now for B, so we're looking for Q sub B. So again, that is 3.8 is equal to 10.64 times, for B, we have 2,400. Then Q sub B raised to 1.85 all over, that is 100. And then diameter of 0.90 raised to 4.87. So we now have the value for QB as that will be 100, that will be 0.9, and this is 24. So 0.647. So 0.647 cubic meter per second. Now for letter C, it's looking for the length of a single pipe having a diameter of 1,000 millimeters to replace A and B with C is equal to 120. So meaning that single pipe will carry the total flow. So first, let's find what is the total flow. So Q is equal to QA plus QB. So total flow is equal to 1.467 plus 0.647. That is 2.114. So 2.114 cubic meter per second. So it will carry this flow for that single pipeline with the diameter of 1000 mm, and then C is equal to 120. So find the length. It's looking for the length of this equivalent pipe. So total of head loss 3.8 equals 10.64 L equivalent. Our Q here is 2.114 raised to 1.85 all over C of 120 raised to 1.85 times the diameter of 1000 mm, that is 1 meter, raised to 4.87. So what is now our LE? Length of the equivalent pipe. That is 3.8 times 120 raised to 1.85 all over 10.64 times 2.114 raised to 1.85. So that is 627.889. So 627.89 meters. So that's for number 6. Let's go to example number 7. A pipeline 300 millimeters diameter, 5,000 meters long, is connecting reservoirs A and B as shown in the figure. To increase the capacity of the old pipeline due to increase in demand, a 300 mm diameter pipeline is connected at its midpoint towards reservoir B. Assuming friction factor is equal to 0.02 for all pipes, compute letter A, the capacity of the old pipeline, B, the capacity of the new pipeline, and C, is it increase or decrease in flow from A to B? So let's find out. So this is the old pipeline, and it will have a new pipeline. So to increase the capacity, a 300 mm diameter pipeline is connected at its midpoint. So at its midpoint here towards reservoir B. So that means there's another connection towards reservoir B. There is the new pipeline. Therefore, we have here pipeline 1, the old pipeline, the original pipeline number 2, and the new pipeline number 3. But they have the same diameter. So as you can see, the old pipeline and the new pipeline has the same diameter. They also have the same friction factor. It's just that they added an extra pipe from the midpoint towards the reservoir. So since the new pipeline is from the midpoint towards the reservoir B, so that means the length of this pipeline 3, the length of this one is half of the total. So that is 2,500. Same is true with the pipeline 2. So it's from the middle, so L is equal to 2,500 as well. And our pipeline 1 is 2,500 meters as well. So since we are given here the coefficient friction factor F, so our formula will be Darcy-Weisbach formula. So we're going to use the Darcy-Weisbach formula for this. So h of f is equal to 0.0826 FLQ squared all over d raised to 5, and that is Darcy-Weisbach. So Darcy-Weisbach formula. So for the total head loss of 50, so what's the first problem? The first one is capacity of the old pipeline. So 50 meters is equal to 0.0826. The F here is 0.02. The length is the total length, the 5,000 meter length, and then the Q of the old one, or the original. So the diameter here is 300 raised to 5. So Q of the old one is equal to 0.121, so that is 0.121 cubic meter per second. So that's for letter A. Now for letter B, what is the capacity of the new pipeline? So it's talking about the new pipeline, that is pipeline 3. So since that's the additional pipeline here, so see here the original pipeline. This is the original pipeline. So 1 and 2 pipe here is R, the original, and this is the additional pipeline 3. So we're looking for Q sub 3 for letter B. So for letter B, what can we see from this, the relationship here? What equation can we make out of it is that Q sub 1, or that is the Q original, is equal to Q sub 2 plus Q sub 3, and that is equal to 0.121. That is equation number 1. And then you can see here that pipeline 2 and 3 are connected in parallel with each other. So head loss 2 is equal to head loss of pipeline 3. This is equation number 2. And then for the total head loss, which is equal to 50, that is equal to the head loss of 1 plus the head loss of 2. And again, that is equation number 3. So what can we observe from pipeline 2 and 3? So what we can already conclude here, since pipe 2 and 3, or pipeline 2 and 3 have the same value, so they have same F length, and we have here the diameter. They have the same diameter, so we can conclude that therefore they are Q2 equals Q3. They have the same rate of flow. So therefore Q1 is equal to twice of Q3, since we're looking for Q3. So twice of Q3. So at 3, So at 3, we have here the total head loss. So what will happen when there is an additional pipe and the total head loss is still the same? So it's easy to conclude that here, since Q1 is equal to twice of Q3, and then you will just divide it into 2 for the value of Q3. But let's see here what will happen to the value of Q3 if we're going to solve it via the head loss. So head loss, so at 3 we have here our head loss is 50, and then we have the same constant 0.826. The F, I think they are the same. Yes, assuming F is equal to 0.02 on all, and the diameter did not change. 0.3, still 0.3 raised to 5. So at equation 3 here, HF1 plus HF3. So we're going to use HF3 there. So that is 2,500, and then our Q1. So for our Q1, that is 2 times Q3 squared. So this is Q1 plus 2,500 of Q3 squared. So what will happen for the value for Q3? Point 3 raised to 5. So that is 73.547. So 73.547 equals, so 2,500 times 2 squared plus 12,500. Q sub 1 squared. So Q sub 3, should say Q sub 3. So Q sub 3 is now equal to square root of 73.547 over 12.5. 47 over 12.5. So 0.077. 0.077 cubic meter per second. Now for letter C, is it increase or decrease in flow from A to B? So let's see. Q1 is equal to twice of Q3. That is equal to twice of 0.077 is 0.154. So 0.154 cubic meter per second. So Q1, the old one, is 0.121 cubic meter per second, is less than Q1 new, which is 0.154 cubic meter per second. Therefore, there is increase. So the answer there is increase of flow. So that's for example number 7. Now for our last example, number 8. From the figure shown, each pipe is 30 meters long of 60 mm diameter cast iron with friction factor of 0.0294. Compute the junction flows in the lines 1 to 4 and their direction. So we're going to solve for the flow, the Q on each pipe here, and we will determine as well their direction. So to determine the direction, that will be let's remember that the flow of liquid, gas, or fluid is from the region of high pressure to the region where there is low pressure. So comparing the pressure from A to junction E, so this is the junction E. Junction E is just 500 kilopascal, so therefore the flow is from the high region to the low region. And that is equal to there. So that is the flow from A to junction E. And then for this B and junction E, since the pressure at junction E is higher than the pressure in junction in point B, therefore the flow is from junction E to point B. And then this one here is lesser than C, therefore the flow is from C to junction E. And then D here is lower than junction E, therefore the flow is away from junction A. So we were able to determine the direction of the flow. Now let's compute for the discharge or the flow rate Q. Since we are given here the friction factor F, therefore we're going to use here the Darcy-Weisbach formula. So the Darcy-Weisbach formula, HF is equal to 0.0826 FLQ squared all over D raised to 5. Okay. So for our head loss, how do we get the head loss here? So our head loss is equal to the head, wherein the head here is the pressure head. So we're going to use here the pressure head. So line 1. So for line 1 here, our head loss 1 is equal to the difference of pressure. So 800, so that is 800 minus 500 all over 9.81 is equal to 0.0826. The F here is 0.0294. 0.0294. It says there that the length is equal. In all pipes, the length is 30 meters and diameter of 60 mm. So that is 30 meters Q1 squared all over 60 mm for the diameter is to 5. So our Q1 is equal to square root of 800 minus 500 times 0.06 raised to 5 all over 9.81 times 0.0826 times 0.0294 times 30. So 0.18. 0.018 cubic meter per second. And the direction here is, the direction of flow of this one is towards junction A. Towards junction E. Okay. For line 2, so that is line 1. Let's go to line 2. So HF2 is equal to, that is 400 and 500. So the difference of the pressure, that is 500 minus 400 all over 9.81 equals 0.0826, 0.0294, 30 Q2 squared all over 0.06 raised to 5. So we have the value for Q2 is equal to, so that is 500 minus 400. And that is equal to 0.0104. So 0.0104 cubic meter per second. And the flow here is away from junction E. Away from junction E. Next, let's go to line 3. HF3 is equal to, so line 3 is 600 and 500. So that is 600 minus 500 divided by 9.81 equals 0.0826, 0.0294, 30 Q3 squared all over 0.06 raised to 5. So what is Q sub 3? So that is 600 minus 500. So again, this is the same 0.0104 cubic meter per second. And the direction here is for junction 3, for pipe 3, that is towards junction E. Last, we have line 4, HF4, that is equal to, so we have here 200 and 500, so 200 and 500. So 0.0826, 0.0294, 30 Q4 squared, 0.06 raised to 5. So Q4 is equal to this 500 minus 200. So 0.018 cubic meter per second. And the direction is away from junction E. So away from junction E. So for checking, let's have all towards junction E. So that is Q1 and Q3. So Q1 plus Q3, is it equal to the away from junction E? Q2 and Q4. Q2 plus Q4. So Q1 is 0.018. 0.018 plus Q3 is 0.0104. Is it equal to Q2 of 0.0104 plus Q4 of 0.018? Yes, they are equal. Therefore, it is correct. So that's number 8. Okay, so that's all for this video.